Hi everybody, welcome to Physics with Dr. T, and welcome to Physics 1, Introductory Physics. In this first lab, we'll be studying basics of motion, position, displacement, velocity, and acceleration. These concepts lay basic foundations of understanding motion and understanding the physics that are either a direct factor or an underlying factor in nearly everything that we do for the rest of the year. So the purpose of the pre-labs is to help bring attention to those aspects of physics that are in your everyday world. And in this week, that's going to be position, velocity, and acceleration. So let's jump into the simulator and take a look at this week's pre-lab activity. So in this week's pre-lab activity, you'll be working with a simulator to just be able to coordinate some motion with graphs of that motion, and we do that with this Walking Man simulator. So when you click on the link in your pre-lab guide, it'll take you to this page, the Moving Man simulator, and you can play with this page a little bit and just kind of get used to him moving around by changing the position, velocity, acceleration that you see here. You can either adjust them by grabbing the toggle, or you can click in the field and type in a value, and when you tab, it moves your character. Tinkering with this for a few minutes will probably be very beneficial to kind of at least see the different motions and give you a little bit sense of understanding the controls. But what we were really interested in is going up here to the charts and click on the charts. And you see that you have the position, velocity, and acceleration here on the left side that you can control. You can control them with the arrows. This is preset values, so you can see the position moves the moving man, even when he's not at start. And then velocity, you can change the velocity either to a negative number or to a positive number. And same thing with acceleration. So now I've played with these, and again, you can type the value into the spot there, but we're going to go ahead and clear this whole thing. We're going to reset everything. And the idea is that you want to, when you push play, it begins the Walking Man moving. Now, we haven't made any settings for the velocity or acceleration, so as this is progressing, you see the moving man is not moving for all this time. This is not an interesting scenario, but what we want to do then is go ahead and change either velocity or acceleration, make those non-zero, and see how that makes an effect. So you can come into velocity, maybe make that 2.5 meters per second, and then tab out of that to a new spot. You see that the arrow jumped to a new position as well. Acceleration, we'll leave it 0. You can push play, and you see that the situation has jumped. There's a little spike where the acceleration went from 0 to non-zero. That's an artifact of the simulation, so don't worry about that detail. And let's say we want to make this a negative acceleration, so we'll say negative 0.5. So we push play again, and now you can see that there's some changes, maybe. It's not obvious. So let's push pause. And I want to direct your attention to these plus signs here. You see that this one right here, the plus, expands and zooms in, zooms out on the horizontal axis. What we're interested in is, can we see any more detail on the vertical axis? So let's click on plus a few times. And even though the spike goes off of screen, we max out our zoom, and you can see that the value here is not 0. It looked 0 when we were really zoomed out. And here, when we look at the velocity, you can see that there's a definite drift downward in the velocity of the Walking Man. And did we see any change in that? It's gone off screen. So it looks like there's some limitations to be able to zoom in there. So play with some combinations and see if you can bring the displacement back. For example, if we want him to have a negative velocity, negative 1.4. And you can see that the top is starting to drift down into it. So I'll go ahead and pause this. This is the general idea. You want to look at the different shapes that the position, velocity, and acceleration graphs each get under certain conditions. For example, if I set the position and velocity to be 0 meters per second, 0 meters and 0 meters per second respectively, and we push play, and you let this begin to evolve, you can see that the position is changing and it looks parabolic, while the velocity is a constant speed change, or a constant change in speed, and the acceleration is a constant value. So hopefully these kind of give you some sense of how changing motion for the position, acceleration, and velocity are affected by the conditions under which the motion is taking place. If you have any questions, you can either email me or your TA, and we'll be more than happy to help you. This first lab may be a little mysterious. So the purpose of doing the labs is so that you can find a way to confirm or demonstrate the theory that you've been studying in the lecture has some physical, real, can be confirmed through physical experimentation. So in this lab activity, you'll have your motion sensor set on one side, and what you'll do with your partner is you'll use a firm board, and you will begin moving backwards, and then you'll go back forward towards the data, which means that you have to think about the different types of motion that's taking place as you're going, and then recognize where the different types of motion is taking place in the data when you go to observe it. Some things that I want to warn you about is that your data may not do what you expect it to. There may not be a perfectly straight line for constant velocity, and your curve for your acceleration points may not be exactly what you expect. So you want to be careful about that. Make sure you take observation to all the things that you're working with. For example, this is obviously a very nice flat smooth board. This can also work, but you notice that there might be some additional challenges to the data when you go to take it. So just some things to think about when you begin analyzing your data. The big question you want to come up with when you look at your data is, what am I looking at? What is this data telling me about in this case, about the motion that you undertook during different segments of time? So once you've got your data, the question is, what do we do with it? How do we analyze it? And you can watch some videos that we've got about how to work with the data in a spreadsheet program. But let's look at the theory side of it for just a minute. Here you see some of the theory that you should have experienced before you arrive in lab. And in this case, we're looking at, again, the basics of motion. So we've got displacement, which we define as a concept that ordinarily might be thought of as distance, but there's an important distinction here. If we consider starting at some point, position A, and we go to position B, we've traveled some distance. But if we also start from position A and go to, say, position C, we can also go the same distance, but you notice that they're not the same location when you get done with your motion. And so there are different values that we can measure. Some of them matter about just how much there is, like temperature. We only care about how hot it is outside. We don't necessarily, there's no important information about a direction that a temperature is going as far as the concept of temperature. Same thing about time. Time is just simply a scale amount. But position can have a big impact if we know what direction that's going. So we look at the distance plus the direction, and so that gives us what we refer to as a vector quantity. So displacement is a vector quantity, and we define it as a change in position. Change in position where delta, we refer to that as delta, or change in position, final minus initial, and 3 lines for equal signs means defined as. After we define displacement, then we can talk about concepts that are related to displacement, things that are of interest, such as a change in position or displacement over some period of time, which we call velocity. Now, you may also be familiar with speed, which would be the scalar quantity of velocity, but velocity itself is a vector. And velocity is change in position over change in time, or final minus initial of position, final minus initial of time. And finally, of these 3 quantities is acceleration. Acceleration is a vector as well. Acceleration is change in velocity over change in time. Delta V, or V final minus V initial, over T final minus T initial. Most of the time, T initial is going to be 0, so it's going to make things a little bit easier, but just be aware that these are basic definitions, and we'll be testing these in this lab activity by looking at how the curve changes throughout the motion that you do and take during your lab activity. So as you become familiar with the equations that you just looked at and the kinematic equations that you're going to be exploring over the next week or so in lecture, you can also become familiar with what the graphs look like related to each other. Here we have position versus time, velocity versus time, acceleration versus time, under 2 different conditions of displacement. Now, there's one more that's actually more or less redundant and doesn't really tell us anything. Obviously, a constant position over time means no motion at all. For example, I am not moving, my position is constant throughout time, so that set of graphs is not informative, doesn't tell us anything new. For a position versus time plot, if you have a constant change of position, you'll get a straight line, and you can do a fit with a function, y equals mx plus b. where m is the slope of this line and b is the y-intercept where it crosses the y-axis. In this example, this line will have a slope, and that slope is represented by the value m when you do your trend line. Well, when you look at your velocity versus time, you'll find that for your velocity versus time, you will have a constant straight line of data that you can fit with also a straight line. But here's the interesting part, is that the slope from this equation, the slope from this graph, y equals mx plus b, position versus time, the slope of this one will correspond to approximately be the y-intercept for the equation of the trend line that fits to this data. And you'll notice that the slope should be close to 0 because it's a horizontal line, which means that the slope of this fit, m, should be close to 0 and correspond to average of 0 from your acceleration versus time for this type of motion. For the part of your data that looks like a curved line for position versus time, a parabola in particular, when you do the fit of this, you'll find that one of the fit values for this curve will correspond very closely to the slope of this line for your velocity versus time, and you should find that your velocity versus time should be a fairly straight line. And your acceleration in that case, for a constantly changing position, should be a straight line, a constant acceleration. At least we want that to be the case. Now, your data is going to reflect some other characteristics, and you want to take some time and think about what might be causing those fluctuations from that straight line, especially as you go into start writing your short lab report. Okay, so in this experiment, your equipment is fairly straightforward. You've got yourself, you've got a large piece of cardboard or poster board that you'll use to hold in front of yourself, and as you're moving, the measurements will be made by this PASCO motion sensor, which uses a passport connection. Now, there are a couple of options on this, which you see here. One is a picture of a person, the other is a picture of a cart. We are not using a cart today, so we're going to make sure that your switch is set to person. And what it basically does is it gives out clicking sound, and the sound bounces off and comes back here, and the passport is able to distinguish how long it took for those particular clicks to arrive from being emitted, and records that data in your PASCO Capstone software. The device that may look a little bizarre on your table is this PASCO 850 universal interface. Now, you're going to be using this throughout the year, so I'll just give you a quick run through on what you have here. So you have a power button. Make sure that you turn your device off when you're done with your experiment. You have digital inputs. Those will come in to use later on. We have analog inputs for particular voltage ranges that, again, will come into play somewhere down the line, most likely next semester, as well as these outputs here. For now, we're going to be using one of these ports. You don't have to choose a particular port. It doesn't have to just be the one. Plug your passport into there, and you put it into one of the ports. It does not click into place. It just seats in there nicely, so just make sure it's firm. And then when you log into Capstone and you click on this port to right-click, it should register it and demonstrate a little miniature image of your motion sensor. When you're ready to begin taking data, you'll first log into the desktop at your workstation, and then once you have fully logged in, you'll find the icon that looks like a rectangle that's got a pyramid sitting on top. It's called Capstone. And double click on that and you'll launch it. It comes into this display screen. You will be using Capstone significantly throughout both terms of physics, so it's a good idea to begin familiarizing yourself with a lot of its features. I want to show you a quick trick so that you can set up your graphs in a kind of nice, easy layout pattern. We click on Hardware Setup, and when it comes up, you should be able to get the moving man. Once you've got that, you come down to the bottom into your record palette, and you'll see that your motion sensor you want to change that to about 50 Hertz so that you can get a good set of data that's nice and smooth and a little bit easier to extract calculations from. So the first thing you want to do once you've got your hardware set up is to go into data summary, and you see you have time here, so you click on the gear when you click on the gear, you have names and symbols, numerical format, labels, errors. We want to go to numerical format. We're going to raise the number of decimal places to about 6 decimal places. This will allow you to have data that you can truncate yourself instead of letting the system truncate it for you and risk coming out with missing significant figures. And you click OK, and you want to do that with the date, with the time, with the position, velocity, and acceleration. You want all the data to come out with multiple decimal places. Then again, you close the data summary, and now you need to have something to display your work. So let's go over to the right hand side. We'll click on graph. You grab a graph, you bring it onto the workspace. Now you notice that there's some gray spots around the workspace that you can go to. We're going to go to the very top one. It's going to place the first graph right there. We'll zoom that up a little bit because we're going to need to make room for 3 graphs. Then we come over and we'll grab a second graph and drag it into the unused space. Again, we want to go ahead and go into the upper bit. It seems like it's scrunched up, so let's stretch it out. We're going to have 3 using the same axis, so there's no reason we can't cover up that single axis. It'll automatically say time anyways. Then we come up and grab the third one, bring it into the workspace, and you notice this time it's going to fill the space. We could go up here, but it just crunches it down. So let's go to the center spot and fill the entire remaining space with the third graph that we need. Grab it by the little dot in the middle and bring it up, and now you see your graphs are all about the same height. If you want to play with it, you just click on the graph that you want to shrink up a bit or stretch a bit, give it the adjustment that you're looking for. And once you're satisfied with your layout, you want to keep the numbers visible. Go ahead and select your measurement. Remember that you want to keep them in a kind of a natural flow of information, so you have position, velocity, and acceleration. So we can either set this as position, velocity, acceleration, or acceleration, velocity, and then position. I'm going to choose position for the first one, velocity or speed for the second one, and then acceleration for the third one. And as I said before, these should all have the same axis, so you can just go ahead and click elsewhere on your space and then begin your data collection. Remember that once you've had a chance to look at the data in Capstone, you've been able to play with Capstone for some analysis, you still want to export your data so that you can go work with it in your own spreadsheet software. You want to create your own graphs, but you can also print this screen out, so that you can have a reference when you're working on it and make sure that you're getting similar results. As far as exporting your data, you also go under File, you scroll down, and you see where it says Export Data, and you click on that, and then it'll have your data selection options. You want to make sure that, again, that your data that you see there has multiple decimal places. You want to be able to preserve that ability to work with the significant figures. So that's the basics of Capstone. Play with it a little bit in the first several minutes of the lab. Take some time to kind of see how it functions and make sure that you're starting to get a feel for this environment. And again, you're going to be working with it for several months, and so it's beneficial to get in there and work with it for several minutes and build a familiarity with how it functions. Make sure that you take time to review the short lab report details that are on D2L. And if you have any questions, make sure that you ask your TAs, and we'll go from there. Well, that does it for this week's lab. If you have any questions, make sure you talk to your TA. You can talk to me. We also have the Physics Help Center, especially when it comes to doing homework and getting some good foundation laid on these basic principles. And until next time, we'll see you in the lab. We'll be studying one of the most fundamental concepts that we begin with most commonly. Come on, do it right. Do it. Okay. I need an eraser to draw my pictures. I won't get bugged on YouTube for this song because it's an original made up by Dr. T. That's me. It's free to hear and sing along. Hi everybody, welcome to Physics with Dr. T. I am Dr. T. That's kind of obvious, right? All right, here goes.
Hang on.
Well,